SocketIO enables real-time bidirectional communication. But what does real-time actually mean? Today's guest is Guillermo Rauch, the creator of SocketIO, a widely used technology for client-server communication. We discuss the nature of real-time apps like Uber and Google Docs, and we talk about the API and the usage of SocketIO. But before we get to our conversation with Guillermo, we'll hear from a sponsor that keeps Software Engineering Daily moving in real time. Thanks for listening. Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. SocketIO enables real-time bidirectional event-based communication. Guillermo Rauch is the creator of SocketIO. Guillermo, welcome to Software Engineering Daily.
Thank you, Jeff. Happy to be here.
Web applications often get described as, quote, real-time, and this can mean a variety of things, including just an empty buzzword. You have said that we don't have a unanimous definition for that term real-time. What is your own definition?
The traditional definition in terms of engineering is you divide systems into soft real-time systems and hard real-time systems. However, when it comes to the web, people have used the term real-time to mean a variety of things. In the context of web applications in particular, it's been tricky to define it. So a lot of times applications have been called real-time when perhaps they update their data maybe every 20 seconds, every 30 seconds. As a matter of fact, the original Google Docs that came through an acquisition that Google made of a product called Writely, I believe, I think it used to update their data every 30 seconds. And it did successfully achieve a certain level of real-timeness or concurrency between the participants, much better perhaps than emailing copies of Word documents as attachments. But then later on, a product called Etherpad came, and I remember in their FAQ they said they were really real-time, with like emphasis on really. And they claimed that they updated their data very frequently, like perhaps between 1 and 5 seconds. So over time, as I was developing these ways of making it easier to create the systems that send data from server to browser and browser to server, I realized that the definition that made the most sense was one that incorporated two things. Your application has to be able to self-update, which means there should be no UI required, so like no refresh button, no pull to refresh, no uncertainty on the user side that the data is updating by itself. So the traditional example here is chat applications, because chat applications never incorporate like a refresh button to like get the newest messages. You never have that sort of uncertainty that it's as recent as it can be, right? And the other thing is real-time systems have to minimize latency. So maybe you're polling every 100 milliseconds and your system can afford to pull it off, or maybe you've implemented server push, so the server lets you know as soon as there is data available that okay, here it is, and the view renders it. But the bottom line is a real-time system has to satisfy those conditions. The data has to update really, really, really fast, and without requiring user interaction.
Would you say that real time is more about what the user perceives rather than giving the user a complete story about what the application state is?
Yeah, perception of speed is one of the most important aspects of this because the limit of transmission of information in the medium that we usually work with is well understood. So, for example, to communicate coast to coast in the United States, the best case scenario over fiber optics would be that you would have a latency of like 50 milliseconds or so. In a lot of applications, of course, you can't achieve the perfect connectivity. You can't achieve, the best conditions for the medium. So, you end up with like scenarios where like it takes you, 300, 600 seconds to like send a packet over. But from the perspective of the user, they know that they committed their data to the system. So, for example, if you're in a chat application and you write a message, you're giving the system your data, and it might take like a second to get to the other participant, right? But you need some sort of instant feedback because you've introduced an input into the system. So in one of my essays that I called The 7 Principles of Rich Web Applications, I claim that you must have an immediate reaction to user input. So in the case of real-time applications, the traditional approach to solve this problem is you insert the message right away, and then you give it a certain, for example, an acknowledgement or a tick, or you improve the message, you enhance the message in some way to say, okay, it's been received by the other party, it's been received by our servers, etc. So much so that, for example, Facebook Messenger nowadays has a 3-state icon next to the message. The first one is like an empty circle, then there's a tick inside, and then it gains a color. So if you think about this, it's a high level of sophistication that they're giving the user, I guess, because there's this idea of several levels of, how committed the message is all the way to the other user when they read it, right? So it's a very interesting approach to solving this problem because you do show the message right away as soon as you like press enter or send, but then you enhance the message over time to communicate that it's actually been sent.
This evolution of the icon, I think this was first in WhatsApp, and I think this was actually one of WhatsApp's killer features, was how it conveyed to the user where the message was in flight. So we're talking about UI stuff when it comes to real time, but there's a much bigger variety of problems to be solved here. So real time applications update with minimal latency, and their updates should occur automatically and uniformly without requiring any interaction. What are the big challenges to achieving this sort of low friction application?
There are several. So from the perspective of achieving minimal latency, we always have to pick the best transport for the data. So that means, for example, if you're using a modern browser and you're in a modern network with no proxies, no firewalls, no filters, no airport, Wi-Fi, you can usually choose a transport that's very efficient in terms of bandwidth usage and in terms of the number of round trips that a message needs to make to be actually, or that the users need to make for them to establish the connection. And in this scenario, perhaps WebSocket or HTTP2 achieve this level of sort of perfection. Or, they're as good as we can get with web technologies, for example. But then in other scenarios, we have to, with SocketIO does this for you automatically, we have to pick the transport that just works, because obviously an application that works always is better than one that works fast only sometimes, right? So we do a lot of work to ensure that the best transport is picked to make sure that the latency is as slow as it can be. But at the same time, we have to guarantee a very high level of reliability. That means dealing with network disconnections and reconnecting automatically, reconnecting in a way where if tons of users are reconnecting at the same time, we're not introducing a denial of service. So all of that is handled for you by SocketIO. And as a developer, you only have to worry about this idea of emitting events back and forth. And an event is simply you give something a name and you attach a data payload to it. And then from the perspective of the application developer, they always have to make sure that in addition to emitting these events, they take care of their UI state in such a way that, like I mentioned earlier, you commit the changes to the screen as soon as you can, regardless of the network. Because the assumption is that the network is more unpredictable, potentially slower. You always have to think about what happens if the message got to the server, but then the server never got back to you because there was some error in the network. You even have to consider this idea that you could be delivering a message more than once. So there are all these like little tricky error scenarios that you have to account for in addition to setting up the real-time communication channel.
So we're going to get to talking about Socket.io, but I want to talk about web development in general a little more. In a typical application, the server is the source of truth, and the client's web page is a partial reflection of that truth. This leads you to the belief that the server should push data to us. How did you arrive at that conclusion?
I arrived to it. It's a very interesting question because I think it's a key point in how most applications architectures should be. Even when you don't have a server, if you have distinct components in your page that are altering local data, you always have to have this idea that you must maintain a central source of truth, and then all your components are listening or are subscribed to it. So the way that I arrived to this conclusion was from the perspective of UX as well. So I set up an application that only listened to incoming events from the network. And then the application, when you were interacting with it, you would, for example, make post RESTful requests to the server. So I would never edit the local state of the application. I would never alter any data directly. I would always wait for the server to respond through some sort of event. So what I arrived to was this really nice architecture where no matter what change I was making, the entire application was always reflecting the latest known truth. And what this meant, for example, is there are no race conditions, there are no edge cases. So if you have several parts of your application that are interested, for example, in showing the latest message from the server, because you have several chat UIs, let's say, or you have several notification counts, you'll never be out of sync because you're always listening on the server. You're not introducing any partial truths in the system that have to be reconciliated as you're listening to events from the server. So there are many scenarios where not using such an architecture, even the user notices that there are lots of inconsistencies. So one is, for example, when in certain UIs, maybe you see an unread message count that is not accurate. You've actually read all the messages and you're like, why does it still say 1? Or maybe the notifications counts are out of sync where the window title says there are 1 unread emails, but then a certain other part of the UI says there are 2. And the most common culprit in this kind of scenario is that you're introducing local changes. So maybe you subtracted from one notification count, but you forgot to subtract from the other one. Whereas when you're listening to events, perhaps from the server or even like a local event emitter that you set up, it's much harder to make such a synchronization mistake.
So in a real-time application, it's important to support reconnection because a user on a mobile device, for example, can have really transient connections. What are some typical problems that developers encounter when they're dealing with connectivity issues?
When it comes to handle connection problems, first of all, I would say detection is the most important one. Depending on what context you're in, for example, if it's a native application or if it's a web application, you can learn about being disconnected faster. So in the case of native applications, the operating system usually has APIs where they're constantly pinging a source of, let's call it like a ping server or a DNS testing server. So they're constantly using several ways to verify that you're connected. And then they display, for example, your connection state on the menu bar icon or whatever. So as a developer, you always have to make sure that you can learn about this global disconnection as soon as possible. In the case of the web, sometimes RESTful requests or XHRs start failing with a specific code that tells you the connection is completely down. So by doing that, you can also improve the messaging that you give to the user. You can almost conclude with a certain level of certainty that is their complete internet connection that's down as opposed to your host being down. In the former case, you would say, please check your internet connection. In the latter, you would say, we're trying to reconnect, please wait. So the important piece here is, if you follow this idea that your entire application is listening on incoming events and the data always updates itself, you have to be very mindful of reconnections because you don't want to insert uncertainty into the system. The user has to have this idea that the data is alive. Communicating that there is an internet problem is very important to that effect, especially when they know that they're expecting some sort of feedback from the server and it's just not coming. They probably start distrusting whether the data is up to date or not. So there are certain APIs that allow this, and the messaging and paying attention to your UI is key. You have to always, when you're designing an application, when you're thinking about how the product works, incorporate this idea of thinking about errors, thinking about reconnections into your system. As an example, I wrote this essay called Pure UI, where you start thinking about designing as creating different states that a component can be in. If when you're doing that explosion of states, maybe you're doing that in your design program or you're doing that on a whiteboard, you must account for error states and reconnection states when you are designing. So if you have different boxes where you're putting your different states, like the user is logged in, the user is inserting a message, the user is befriending someone, always think about actually that action might fail. One of the things that I've been thinking about lately is in the future, design programs might want to incorporate this idea of guiding you through what you're actually missing in your design. Why? We know that whenever the network is involved, failures can occur. There's no such thing as a perfect, never fails network, right? So every time you're thinking about transitioning from states, if the network is involved, then absolutely you have to account for an error. And nowadays, design programs don't enforce this. Not even developers enforce this because sometimes they choose to not handle errors at all. And sometimes you're oblivious to the other levels of error handling that you could be doing. For example, this idea of global error handling when the connection is not working well. You have to notify the user with some sort of global banner or something that says, nothing is working right now, the internet is disconnected.
Yeah, I like this idea of giving the user some UI cues about their connectivity and how that might be affecting the application. So I watched a talk from you, and you explored some of the aspects of TCP that developers should keep in mind as they're developing these, what they call real-time applications, often single-page applications. And many developers, including myself, don't know much about how TCP works. What are the important consequences of TCP that we should be thinking about as we are trying to build real-time applications?
Yeah. As I continue to explore this idea of real-time applications, I realized that looking at latency in a particular interaction is not sufficient. So, for example, you look at how long it takes to send a message, but you can't forget to look at how long it takes to load the application to begin with. So, this total view of latency is one that I incorporated in thinking about real-time systems. So, it allows you to explore the entire experience from the edges. The edge that most web applications first face, for example, is that you load the website or you get a URL and you click it. So that's where you have to start analyzing the real timeness of your application as it relates to minimizing latency. The example that's crucial there is when the page is first loading. Let's assume that the user has never been to the website before, that no tabs were open to this website before. Then the connection is first established. So a TCP connection is established from your computer to the target host. And here is when TCP has this idea of congestion control. So TCP tries to start slow and then incrementally become faster as a way of protecting against congestion and protecting against too much traffic that can actually not be handled, preventing against users sending more data than the server can handle, etc. So since TCP starts slow, you have to be very mindful of that initial page load time, even more so than before, because now you know that if your page was really heavy, now the user is not only as the user have to download a big page, but it's actually also starting slow. So it comes down as a cue for developers. It comes down to focusing on the first 14 kilobytes. That's the traditional recommendation that will work in most networks, will work well with most setups and browsers. If you focus on the first 14 kilobytes, and you have to make sure that you deliver the data that the user was interested in those 14 kilobytes. If you're creating a news site, that means that in the first 14 kilobytes, you probably want to have the first portion of the content of the news story. If you're developing a chat application and you're linking to a specific conversation, you want to load that conversation. So single page applications here, in many cases, have been at fault because they take too long to load initially. They sometimes request the data only after they've been loaded, and in other cases, they just display a white screen until everything loads. So it's like kind of like this really awkward flickering effect. But it all comes down to you have to make sure that you load that initial payload of the data as soon as possible.
I love being a software engineer because of how easy it is to build side projects. And I've built countless side projects. I've built a social gambling application, a dating website backend that had 0 users, a stock trading music rhythm application for Android. And I think every developer should have side projects. So when I have a web app that I want to deploy and share, I want to show my friends my most recent project that nobody will care about, I use DigitalOcean to quickly spin up a server and host my projects. And who knows, if one day one of my apps takes off and goes viral and people actually do care, I can easily scale using DigitalOcean's flexible pricing plan. Companies like TaskRabbit that have grown rapidly have used DigitalOcean for this very reason. But until this happens, I will happily stick with the $5 a month plan. Sign up with promo code SEDaily to get a free $10 credit as a listener of our show and start building your apps. We would love to see what listeners build, so send us an email showing us your project. I've also interviewed Moise Uretsky, who is the co-founder of DigitalOcean, and he mentioned that the ease of use and the flexibility is why they built the service in the first place. That DigitalOcean interview is one of my favorite episodes. Moisey talks about bleeding in a data center. He says, you don't know how hard it is to do a cloud hosting service until you've bled in a data center. It's really interesting. So speaking of which, let's get on with this episode of Software Engineering Daily. So now that we've discussed real-time in general, let's talk about Socket.io. What is Socket.io?
Socket.io is a little library, both for servers and clients in a variety of programming languages, that allows you to model your communication as events in a bidirectional channel. This means that server can emit events to clients and client can emit events to servers. As a matter of fact, now we're exploring the possibility between clients emitting events to clients directly through peer-to-peer communication that will be extremely relevant in IoT. But the bottom line is you can model communications as events they contain a name, like some sort of identifier that gives the action its meaning or its purpose. And then there is a data payload that can be any sort of JSON data structure. It can be a string, or it can be binary data as well. So a lot of people are even doing uploads over this system where they have a much more fine-grained control over how much data is sent, how big the chunks, etc.
So is the socket of Socket.io, does that refer to a WebSocket?
Yeah, so SocketIO is transport agnostic. It started with WebSocket just being spec'd out, and we had a technique for mimicking it, which was called long polling. So the nice thing about long polling is it has very similar performance characteristics. It's not as fast, and it always works. So it's almost like a technique for using Ajax in a very creative way. So SocketIO takes that as a starting point because, as I mentioned earlier, as a focus on reliability is one of our priorities, then we want to make the connection always work in the context of any client, any network, any proxy that might be in place. And then we try to upgrade to the most suitable transport in terms of performance, which could be WebSocket. So we've extended this idea, and since from your perspective, you're just emitting events back and forth, the transport becomes less relevant. So, and we can basically hide that complexity from you, and we can innovate also in what transport we can add in the future. So WebRTC allows us to transport data directly from peer-to-peer, which in some cases can have tremendous latency advantages or privacy advantages. In other cases, we could explore Bluetooth as a medium. So the bottom line is the transport is less important when you're developing the application. What you care about is the data. So we've created SocketIO to make real-time data flow as fast as possible and as reliable as possible.
In Socket.io, the client and the server both have an API. Can you describe those APIs for the client and the server?
Yeah, so the way that you subscribe to events is very similar to the DOM. So, when you do document.add event listener click, you're listening for incoming data. In this case, the incoming data is the position of the click, what element it was on, etc. So from the server side or the client side, since it's bidirectional, you say socket.on, and you listen on a certain event. And then to emit on the DOM, usually the emit is done on your behalf by the browser because you click and the event is emitted for you. But the DOM calls that API trigger event. So if you wanted to create a synthetic event, you would say document.trigger event, click, and then like 20 arguments. And on SocketIO, the equivalent would be socket.emit. So you can say socket.emit to the server, or the server can say socket.emit to the client. The server has an advantage in that the server is aware of many clients. So the server has this idea of broadcasting. You can say, I want to emit an event to a room. So you can say, this half of the clients are in this room, this half of the clients are in this room. Or you can say, I'm going to emit an event only to people that have been authorized. So you might want to use this idea of channels or rooms to do authorization. So you say only users that have been put in the group admins will receive this alert, for example. So the bottom line is the API is very simple. It's just events, but the server has the idea that it can broadcast to everyone, to a group, or to just one user.
In web application development, we often want a persistent connection between the client and the server. What are the challenges to this, and how does Socket.io help achieve it?
The challenges are many. So first of all, a lot of the persistent connection transports are very low level. So for example, WebSocket doesn't give you the flexibility to send JSON even. You have to always like create a little protocol on top where you say, I'm going to always send this type of JSON packet with a certain like name, etc. The other thing that it doesn't do for you is reconnecting. So sockets by default are very simple. They have an error state, they have an opening state, and they have a closing state. But there's no such thing as it'll reconnect, it'll give me a notice when it's reconnecting so that it can tell the user, etc. So Socket.io makes that persistent connection a lot more, let's say developer friendly, because we're thinking about how to use that persistent connection for building real applications.
In a talk that I saw on YouTube, you emphasized events and how events play into the Socket.io model. Could you explain how events are at the center of push-based systems?
Yeah. When you open a persistent connection, you usually have this idea that you're sending bytes, like just like raw bytes over the wire. In the case of WebSocket, it started even only being able to send strings, like UTF-8 encoded strings. So you could only send a message that said like hello or any, or perhaps a number. But there's no way for you to like send a packet unless you create an object, you serialize it, and then on the other side you deserialize it and you inspect that object and you say, well, what is this user trying to do? Are they trying to send a message? Are they trying to like say that they're connected? Are they trying to log out? So the idea is events become the organization of this byte stream over this persistent connection. They're very key also to the architecture that I mentioned earlier, that if you're listening on incoming events, you're listening on this one source of truth, and it makes your application much easier to reason about, as opposed to you performing intermediate data changes in your local state and then like trying to reconciliate later on when you hear from the server. One always has to be aware that conflicts can occur when you have disparate sources of data, right? Kind of like when Git, you push and you say, oh no, something changed, and you have to like work on the conflict. So events provide a very nice organization over persistent connections, and that's why we chose them. We think they're also a very fundamental way of thinking about systems. You can find the event emitter on the DOM. You can find the event emitter on most other, even like 20-year-old GUI systems. Events are a very easy to grasp, very easy to understand way of looking at our world even.
So I'd like to give a small example of the type of application that Socket.io makes easier. So let's talk about a chat application. In the past, a chat application might have been built using PHP or the LAMP stack, and there were certain difficulties in using that type of stack. So could you give us an idea of what those difficulties were and how Socket.io improves on the past model of client-server interaction in something like a chat application?
Yeah. So in the case of a PHP chat application, you almost have no way of this idea of sending something from the server to the client. So an example would be if you receive a message from a certain user, and you handle that with, say, message.php, and you get the data about the message. Let's say that the message says, oh, this is targeted for a private DM to this other user. So as a server, and this is why I mentioned earlier, the server becomes usually the first to know about the truth changing, or the first to know about the data changing, right? Other than the user that sent it. So in an ideal world, the server would be the one that sends that message directly to its recipient. And that's where the first complexity arises with a model like PHP's. There is virtually no way when you get to use the LAMP stack that you can say, okay, now give this message to this user. You have to necessarily wait for that user to request it later on. So not only are you starting to pay a latency penalty there, you start to pay an engineering penalty, because now you have to model your client as, let's wonder about what messages are coming every number of seconds, right? So you have to build all of that yourself, whereas with SocketIO, you just say, broadcast this message to this one client or to this one room, and then you know that the instant that those clients connected over the socket, they subscribe to those messages, and they're going to come as events. So that's where the bidirectional part of it comes, and it's such an improvement in terms of performance. And also, it'll make things easier to write for you. You are able to send events from the server to the client, and not just from the client to the server. In a world that's moving a lot towards push as opposed to pull in almost every aspect of communications, marketplaces, even the economy, you have to consider that by switching this around, you improve your architecture, you improve your responsiveness, and you improve the user experience.
So you've said that the mission of Socket.io is to make real-time apps possible in every browser and mobile device, blurring the differences between different transport mechanisms. And you've touched on this earlier in our conversation. What are some of the challenges to getting this consistency across different platforms?
I would say the main challenge has to do with every operating system, every browser, every mobile device will have different networking APIs. So that's the first one. You have, to implement different APIs for different configurations. But then it's not just that particular device or that particular OS that will determine that how the communication is going to work. There's always the opportunity for other layers to come in later on and actually ruin your communication experience. So, for example, if the connection is unencrypted and you have a proxy that doesn't understand a certain transport or doesn't like connections of a certain length, or there are many different failure scenarios that can be introduced by, for example, corporate proxies, then it's not even just about you picking the right API and making it work correctly. You start to realize that there could be errors that are introduced by other layers of the stack. So that's why we take this multi-transport approach, where we can seamlessly transition between transports if the network is not behaving correctly. So it's not just about making the decision to choose the right API, it's also about how is this API interacting with the external medium. And that, I would say, is the biggest complexity. For example, when we worked on peer-to-peer event systems, we realized that we can't always achieve a peer-to-peer communication, so we use the cloud as a fallback. And in this way, what we get is a very reliable communication experience for the user and more input to the developer about the potential latency characteristics of the medium. So if you're achieving a peer-to-peer connection, you can communicate that to the user in some way, because, again, it could have privacy implications as well. And if it falls back to the cloud, your application continues to work. So this is the promise that we give our users with SocketIO. We always make it so that the connection works.
So I want to talk some about what you're working on today. You're working on a product called Micro. Could you tell me more about this?
Yeah, so Micro is our latest open source project that allows the microservice architecture. Basically, when you write a service nowadays, you tend to conflate a lot of different routes, a lot of different behaviors, a lot of different concerns into a single process or a single repository or a single monolithic application. So for example, if you have a post/payments API call and you have a post/logout call, you tend to put that in the same place. Micro is an approach for writing services where the concern is a single API endpoint. So instead of writing, a monolithic application, then you make that listen on a single port. Let's say you put it on api.yourcompany.com. The approach that over time we've found works really well is every API endpoint ends up being its own independent HTTP service. And then we use a technology like Nginx, for example, to route requests to the different microservices. So from the developer that's querying your API, they think they're going to api.yourcompany.com/payments, but underneath it's going to its own specific microservice, perhaps hosted at like payments.yourcompany.com. So by putting every API endpoint into its own microservice, what you get is greater debuggability because you can take a look at a specific service per service approach, to look at the logs, for example. It's easier to test because now you write tests in your repository only for that API endpoint. I've seen a lot of companies in it where 90% of their traffic goes to a single endpoint. So it doesn't make sense to, sometimes you don't even want to look at the logs from others. And finally, something that's really awesome is you can scale these microservices independently. So you might need 100 nodes for a certain API endpoint. You might need one for another. And finally, error debugging becomes a lot easier because if a failure happens on a given microservice, it has no bearing whatsoever in another one. And you can restart them independently. You can then later on debug them independently. Micro makes it so that when you write your code, if you've written Node.js or JavaScript before, all you do is you export a function that takes the request and the response as parameters. And that's all there is to it. The way that we do this is because with ECMAScript 7 and with certain features introduced in ECMAScript 6, we've gained the async and await keywords that drastically simplify how we manage asynchronous services. The other thing to consider when you look at microservices nowadays or APIs nowadays is they usually involve calling other microservices or calling other APIs. So if you have a subscribe endpoint because you have a form or you sign up or whatever, it's likely that you're also going to send a subscription request to MailChimp, for example, or to other newsletter providers. So somewhere in your backend, you're going to make an API call. The bottom line is there's usually asynchronous behavior happening in these microservices. With the async and await keywords, we make this code that used to be very gruesome to write, that used to involve a callback soup, because you had to nest all these API calls and pass callbacks down below. We basically make it seem like it's synchronous code while not tricking ourselves, because you have to write, for example, await request, and you make your request. So you're being explicit that you're performing an asynchronous request, and your code looks a lot more sane because every line is describing the timeline of everything that's occurring in that particular API endpoint. And that ties really well into the architecture that I mentioned earlier on, because from those microservices, you can now use something that we call the SocketIO emitter. You can launch broadcast events from these microservices. And the SocketIO servers become independent to scale from your HTTP endpoints. This brings a really great way of integrating things that were seemingly impossible to integrate before. Now you can emit SocketIO events from any sort of backend node that you have, not just the one Node.js SocketIO server. And we think that this architecture will make it possible to integrate real-time behavior to a lot of different paradigms, including like a PHP backend, including Java backends, that by themselves cannot really establish a real-time channel. We can basically plug a SocketIO node to it, and they can communicate seamlessly. So from the perspective of the user, they connect to the SocketIO server, but the SocketIO server is receiving events that it will be sent along to the user from any other backend piece. So it could be a microservice, it could be another Node.js service, etc. The bottom line is we've made this idea of sending events possible from any backend node that your application might have.
Great. Well, that's a really exciting development. Seems like a good place to close off. Thanks for coming on the show, Guillermo. It's been a pleasure talking to you. I'm following Micro closely, and I'm a big fan of Socket.io. So appreciate you coming on the show.
Thank you.